In this video, let's delve deeper and get even better intuition about what the cost function is doing. This video assumes that you're familiar with contour plots. If you're not familiar with contour plots or contour figures, some of the illustrations in this video may or may not make sense to you, but it's okay, and if you end up skipping this video or if some of it doesn't quite make sense because you haven't seen contour plots before, that's okay, and you still understand the rest of this course without those parts of this. Here's our problem formulation as usual with the hypothesis, parameters, cost function, and our optimization objective. Unlike before, unlike the last video, I'm going to keep both of my parameters theta 0 and theta 1 as we generate our visualizations for the cost function. So, same as last time, we want to understand the hypothesis, h, and the cost function j. So here's my training set of housing prices. And let's pick some hypothesis, like that one. This is not a particularly good hypothesis, but if I set theta 0 equals 50 and theta 1 equals 0.06, then I end up with this hypothesis down here, and that corresponds to that straight line. Now, given these values of theta 0 and theta 1, we want to plot the corresponding, cost function on the right. What we did last time was, when we only had theta 1, we were drawing plots that look like this as a function of theta 1. But now we have two parameters, theta 0 and theta 1, and so the plot gets a little more complicated. It turns out that when we had only one parameter, the plots we drew had this sort of bow-shaped function. Now, when we have two parameters, it turns out the cost function also has a similar sort of bow shape. And in fact, depending on your training set, you might get a cost function that maybe looks something like this. So this is a 3D surface plot where the axes are labeled theta 0 and theta 1. So as you vary theta 0 and theta 1, the two parameters, you get different values of the cost function j of theta 0 comma theta 1. And the height of this surface above a particular point of theta 0, theta 1, right, that's the vertical axis, the height of the surface at the point indicates the value of j of theta 0 comma j of theta 1. And you can see it sort of has this bow-like shape. Let me show you the same plot in 3D. So here's the same figure in 3D with axes theta 0, theta 1, and vertical axis j of theta 0, theta 1. And if I rotate this plot around, you kind of get a sense, I hope, of this sort of bow-shaped surface. That's what the cost function j looks like. Now, for the purpose of illustration, in the rest of this video, I'm not actually going to use these sorts of 3D surfaces to show you the cost function j. Instead, I'm going to use contour plots, or what are also called contour figures. I guess they mean the same thing, to show you these surfaces. So here's an example of a contour figure shown on the right, where the axes are theta 0 and theta 1. And what each of these ovals, what each of these ellipses shows is a set of points that takes on the same value for j of theta 0, theta 1. So concretely, for example, let's take that point and that point and that point. All three of these points that I just drew in magenta, they have the same value for j of theta 0, theta 1. Okay, this is a theta 0, theta 1 axis, but those three have the same value for j of theta 0, comma, theta 1. And if you haven't seen contour plots much before, imagine, if you will, a bow-shaped function that's coming out of my screen, so that the minimum, so the bottom of the bow is this point right there, right, the middle of these concentric ellipses. And imagine a bow shape that sort of grows out of my screen like this, so that each of these ellipses has the same height above my screen, and the minimum of the bow, right, is right down there. And so the contour figures is a way to, maybe a more convenient way to visualize my function j. So let's look at some examples. Over here, I have a particular point, right? And so this is with theta 0 equals maybe about 800, and theta 1 equals maybe a minus 0.15. And so this point, right, this point in red corresponds to one particular pair of values of theta 0, comma theta 1. And they correspond, in fact, to that hypothesis, right? With theta 0, it's about 800, so this intersects the vertical axis around 800, and this is a slope of about minus 0.15. Now, this line is really not such a good fit to the data, right? This hypothesis, h of x, with these values of theta 0, theta 1, it's really not such a good fit to the data, and so you find that its cost is a value that's out here, that's pretty far from the minimum. Right, so it's pretty far, this is a pretty high cost because this is just not that good a fit to the data. Let's look at some more examples. Now here's a different hypothesis that's, still not a great fit to the data, but maybe slightly better. So here, right, that's my point. Those are my parameters, theta 0, theta 1. And so my theta 0 value, right, that's about 360. And my value for theta 1 is equal to 0. So, let's write that out. This theta 0 equals 360, theta 1 equals 0. And this pair of parameters corresponds to that hypothesis, corresponds to a flat line, right? This is h of x equals 360 plus 0 times x. So that's my hypothesis. And this hypothesis, again, has some cost, and that cost is, plotted as the height of the j function at that point. Let's look at just a couple more examples. Here's one more. At this value of theta 0 and at that value of theta 1, we end up with this hypothesis h of x. And again, not a great fit to the data, and we just actually move even further out for the minimum. Last example. This is actually not quite at the minimum, but it's pretty close to the minimum. So this is not such a bad fit to the data, where for a particular value of theta 0, which whatever this value is, and for a particular value of theta 1, we get a particular h of x. And this is not quite at the minimum, but it's pretty close. And so the sum of squares errors, the sum of squares distances between my training examples and my hypothesis, really that's a sum of squared distances, right, of all of these errors. This is pretty close to the minimum, even though it's not quite the minimum. So with these figures, I hope that gives you a better understanding of what values of the cost function j and how they are, and how that corresponds to different hypotheses, as well as how better hypotheses may correspond to points that are closer to the minimum of this cost function j. Now, of course, what we really want is an efficient algorithm, like an efficient piece of software, for automatically finding the value of theta 0 and theta 1 that minimizes the cost function j. Right? And what we don't want to do is to have to write software to plot out this point and then try to manually read off the numbers. That's just not a good way to do it. And in fact, we'll see later that when we look at more complicated examples, we'll have higher dimensional figures with more parameters. That it turns out we'll see later in this course examples where this figure cannot really be plotted, and it becomes much harder to visualize. And so what we want is to have software to find the value of theta 0, theta 1 that minimizes this function. And in the next video, we'll start to talk about an algorithm for automatically finding that value of theta 0 and theta 1 that minimizes the cost function j.